The ground beneath North America's west coast is holding a silence longer than modern memory, but the tension locked inside it just reached a threshold never recorded in human history. A major scientific reconstruction published last month has delivered a stark conclusion that reframes the subterranean hazard facing millions. After tracking a full millennium of tectonic movement, researchers established that stress accumulated along our region's most dangerous fault network has reached its absolute peak, higher than at any point in the past 1,000 years. We are living directly on top of a continental fault system loaded past every historical limit on file. In recent weeks, reports of violent ruptures globally led many to ask if the planet is entering an active cycle. The short answer is no. The Earth is not waking up, and global background seismic rates remain unchanged. What changed is our capability to measure exact physical stress stored inside specific, heavily populated fault junctions, and the number returned by the instruments is not reassuring. To understand what this finding means, we must execute a critical correction. Popular media frames this hazard as an overdue monster waiting for a specific calendar date. But geology does not work on an alarm clock, and overdue obscures the real physics. The true story is about an energy balance. This research establishes a measurement of force, identifying an unlocked structural junction where two distinct fault systems sit close enough to chain together into a single cascading rupture. By examining the data, we trace how a slip event on one segment jumps to another, why longer ruptures dramatically increase shaking duration, and how engineering choices determine whether a magnitude 7.5 event results in minor disruption or catastrophe. When a silent continental fault system reaches a 1,000-year stress peak, what actually happens to the cities sitting in its path? The investigation was led by a research team affiliated with the University of Bern in Switzerland, collaborating with field geologists reading the physical record of past continental ruptures. Stress is invisible. You cannot place a physical pressure gauge 12 kilometers underground to read proximity to catastrophic shear failure. Instead, the team constructed a physics-based four-dimensional model mapped by three independent empirical lines: precision radiocarbon dating from trenching sites, tree ring chronologies preserving seismic shock signatures, and documented historical records of known slip events. Braided together, these datasets allowed the model to run the physical clock backward across 10 centuries, calculating strain released during past ruptures and force quietly accumulating since. A single earthquake is an isolated data point, but a 1,000-year reconstruction reveals the baseline rhythm of a fault line, the rate at which it loads, bends, and breaks. When researchers plotted the present day against that 1,000-year baseline, the current moment sat at the absolute top. Stress stored along these primary structural zones has officially passed every peak recorded since the year 1026. One precise zone stands out above all others. The section running through the mountain pass near San Bernardino recorded a stress value of roughly 3.6 megapascals, the highest concentration of tectonic force anywhere in the 1,000-year timeline. Directly adjacent, the primary continental boundary tells a story written entirely by silence. The last major rupture along this southern segment occurred in 1857, an event estimated at magnitude 7.9. In the 169 years since, tectonic plates continued grinding past each other at approximately 5 centimeters per year. For over a century and a half, that lateral motion has been absorbed, bending the deep crust like a massive mechanical spring coiled tighter every month. What makes this finding critical is that two separate fault systems reach their 1,000-year peak at the exact same moment, directly where they converge. That convergence point is Cajon Pass, a mountain corridor roughly 80 kilometers northeast of urban centers. Beneath this infrastructure corridor, two primary fault traces draw within kilometers of each other, creating an active earthquake gate. Under normal conditions, when a fault ruptures, the fracture stops when it hits a structural boundary where rock geometry shifts, or where an adjacent segment carries different internal stress. That variation acts as a natural break, trapping the earthquake within a single segment. The gate remains closed. However, when two adjacent fault systems are loaded to identical peak stress levels simultaneously, that natural break fails. Instead of halting the rupture, the junction allows the stress wave to jump across the gap, chaining two networks into one continuous mega-rupture. The break is gone. The gate is unlocked. If a rupture jumps that gate, researchers estimate the resulting seismic event could reach magnitude 7.4 to 7.8. The moment magnitude scale is logarithmic. Each whole unit step represents roughly 32 times the energy released. A magnitude 7.5 event unleashes 30 times the destructive power of a 6.5. Placing a multi-segment failure of that scale beneath transport corridors, residential neighborhoods, and critical utilities means threat encompasses an entire economic basin simultaneously. Furthermore, longer ruptures create a secondary hazard: duration. A moderate tremor shakes the surface for 10 seconds, but a multi-fault rupture unzipping segment after segment can shake the ground for a full minute or longer. Structures engineered for 15 seconds of acceleration experience catastrophic fatigue when shaking persists for 60 seconds. When weak first stories buckle and unreinforced masonry fails. This finding is not a calendar prediction. The model cannot supply a date or time. That gap between knowing a fault is loaded and knowing when it will fail is why structural readiness matters far more than prediction. Millions live within the direct shaking zone. Across older urban corridors, thousands of soft-story residential buildings remain highly susceptible to lateral shear forces. High-pressure gas mains, water conduits, and electrical corridors cross active fault traces at multiple points, creating immediate fire risks following an initial shock. Yet modern structural codes, construction standards, and real-time early warning systems alter the survival baseline. Systems like Shake Alert detect non-destructive primary P waves racing ahead of an earthquake, broadcasting automated alerts before slower, destructive secondary S waves hit urban centers. Depending on distance from the epicenter, that provides seconds to a minute of lead time, enough for automated systems to slow rapid transit trains, trigger emergency shutoff valves on fuel lines, isolate power grids, and allow residents to take cover. Seconds save lives. The life or death variable is how fast we close the gap between old structures and modern engineering standards. That reality was demonstrated twice earlier this year. On June 24th, two powerful earthquakes struck the coast of Venezuela within 39 seconds of each other. The primary shock registered at magnitude 7.5 at a shallow depth of 10 kilometers. In coastal corridors near Caracas, structural failure was widespread, with reporting indicating nearly 80% of local buildings collapsed. Fatalities climbed into the thousands. Unenforced building codes, aging infrastructure, and absence of early warnings transformed a geological event into human catastrophe. Contrast that devastation with an almost identical event off the Sanriku coast of Japan. That offshore event measured magnitude 7.4 at the exact same shallow depth of 10 kilometers, triggering tsunami warnings and evacuations. By every physical measurement, it was identical to the Venezuela event. The outcome resulted in 2 minor injuries, 0 fatalities, and 0 structural collapses. The difference was decades of enforced engineering standards, base isolation building technology, automated train braking systems, and a real-time early warning network. These events deliver an unmistakable lesson. A fault line loaded to a 1,000-year peak is a physical reality, but human outcome is determined by preparation. We cannot prevent stress accumulation, but we can control infrastructure integrity, retrofit speeds, and individual readiness. To track how this situation unfolds, observers should watch 3 specific indicators: whether localized microseismicity begins migrating directly into the Cajon Pass junction, whether regional geological survey bodies adjust long-term probability models, and whether municipal authorities accelerate funding for structural retrofits on soft-story housing and trans-fault utility lines. On the morning of January 9, 1857, residents along the southern expanse of the fault system witnessed a surface disruption that redefined structural geology. The ground opened along a continuous tear 350 kilometers long, shifting laterally by up to 9 meters. That Fort Tejon rupture was the last time the southern strike-slip network released stored mechanical energy. For 169 years, no major surface rupturing event occurred along that primary line. A stretch of rock that historically relieves strain every 9 to 10 decades has sat completely frozen through 5 generations of industrial expansion. The primary plate boundary on the western edge of North America is a transformed system driven by the Pacific Plate sliding northwest past the North American Plate. This lateral grinding is distributed across a complex multi-fault network. Further north, that same machinery drives the Cascadia subduction zone off Vancouver Island, silent since January 26, 1700, and the Queen Charlotte Fault off Haida Gwaii, which generated a magnitude 8.1 earthquake in 1949, the largest instrumentally recorded failure in Canadian history. In the southern sector, two massive lines dominate, the main strike-slip boundary and the San Jacinto Fault Line. Historically, these systems operated like a paired mechanical relief network. Records reconstructed by teams at Natural Resources Canada and international surveys show that when one fault locked, the other bled off strain through periodic moderate ruptures between magnitude 6.0 and 7.0. Broad public reporting refers to this quiet period as a static delay, a waiting game where a fault gets overdue like a delayed train. But in solid mechanics, a locked fault is not standing still. Tectonic plates move continuously at approximately 50 millimeters per year. When the surface trace is locked by friction, deeper crust continues to creep, stretching the elastic upper crust like a sheet of steel pulled from opposite ends. The accurate way to view this quiet period is as continuous energy loading. Across the last 1,000 years, major slip events on the southern transform system occurred with a baseline recurrence interval of every 100 to 130 years. At year 169, the system has exceeded its average historical recurrence window by more than half a century. In early decades of seismic monitoring, hazard models relied on instrument networks installed in the mid-20th century, capturing only a brief snippet of geological time. Engineers designed infrastructure assuming earthquakes within historical mid-range intensities. Recent research reconstructed that 1,000-year baseline by combining paleoseismic trench data, tree ring growth signatures, and radiocarbon dating to map major failure events back to the early medieval period. When historical rupture values were plotted into a four-dimensional stress evolution model, mechanical stress historically fluctuated within a defined band, rarely exceeding 2.5 to 3.0 megapascals before a rupture occurred. Today, localized mechanical stress near key junctions reached roughly 3.6 megapascals, a level absent from the 10th-century log. Translating spatial scale into concrete terms illustrates the volume of rock under strain. The loaded region spans over 400 kilometers, a distance equivalent to driving from Vancouver to Kamloops or Toronto to Ottawa, reaching 12 kilometers into the brittle upper crust. Applying 3.5 megapascals across millions of cubic meters of rock creates total elastic strain energy equivalent to thousands of megatons of continuous mechanical force. If baseline data used for engineering standards was drawn when the system was half loaded, design assumptions are dangerously low. This issue is not confined to foreign jurisdictions. Transform fault dynamics share fundamental physics with coastal structures across North America. The episodic tremor and slip events monitored by Ocean Networks Canada beneath Vancouver Island, deep crustal strain on the Leech River Fault beneath Victoria, and seismic hazards of western Quebec and Charlevoix seismic zones in eastern Canada rely on the same principle. The longer a locked fault exceeds its average recurrence baseline without releasing strain, the larger the eventual rupture area must be to clear the backlog. A single number flashing on a terminal screen inside a seismic monitoring laboratory in Bern, Switzerland, captured the moment a fundamental assumption in continental physics broke down. 3.6 megapascals. It was the output of a four-dimensional stress model reconstructing 10 centuries of crustal deformation. Public commentary describes seismic risk as if a fault line were a wooden beam that snaps when bent too far. That framing is incorrect. A major fault system is a friction-locked boundary zone composed of thousands of overlapping rock segments. Earthquakes happen when static friction along an existing fracture plane converts into dynamic sliding friction. At depths between 5 and 15 kilometers, the brittle upper crust is held together by immense lithostatic pressure. Along a transform boundary, tectonic plates try to slide horizontally past each other. Where rock faces press together, asperities lock into place, creating static friction. As the mantle continues convective drive, surrounding crust deforms elastically, storing potential energy as shear stress. Under normal conditions, an earthquake begins at a discrete hypocenter where shear stress overcomes static frictional strength of a single locked segment. Asperities snap, static friction drops to dynamic friction, and stored elastic energy is released as a propagating rupture front traveling at 3 kilometers per second. Normally, that rupture front encounters a structural barrier, A bend, step-over gap, or region with lower shear stress, which acts like a thermal break, absorbing kinetic energy and capping magnitude at 6.0 or 6.5. The breaking point occurs at Cajon Pass, where two primary fault systems draw within kilometers of each other. In old seismic models, Cajon Pass was treated as a permanent closed gate. Those models assumed fault lines loaded independently. If fault A was near its stress peak, fault B would be at a lower state, acting as a barrier. The Bern research team, using GPS telemetry, strainmeter arrays, and paleoseismic trench records, proved that assumption wrong. For the first time in 1,000 years, both parallel fault systems reached maximum shear stress simultaneously. When both sides of a step-over gap are loaded to 3.6 megapascals, the structural barrier disappears and the thermal break fails. When a rupture initiates on the primary strike-slip line, the dynamic stress wave hits an adjacent fault resting on the edge of failure, triggering instant failure on the second fault. An unlocked gate transforms two separate magnitude 7.0 events into a single mega-rupture reaching magnitude 7.8, unzipping along a 350-kilometer tear. This evidence is backed by physical measurements from borehole strainmeters embedded hundreds of meters in bedrock. Monitoring arrays operated by Natural Resources Canada and International Geological Surveys track these shifts in real time, confirming deep elastic strain across the western margin is accumulating without corresponding creep or silent slip offloading. At 14:32 Pacific Standard Time on a typical weekday, over 70,000 vehicles per hour pass directly through the Mountain Pass corridor near San Bernardino, moving along interstates, rail arteries, and fuel conduits directly across the friction-locked boundary. Not one commuter feels the 3.5 megapascals of shear stress 7 kilometers beneath their tires. But when that subterranean gate unlocks, physical transformation of that transport corridor will occur in less than 40 seconds. Popular commentary focuses on cracked pavement or swaying buildings, but the real threat of a magnitude 7.8 multi-fault rupture is systemic collapse of interconnected continental infrastructure. When a multi-segment failure unzips across 350 kilometers of terrain, it severs lifelines supplying water, electricity, fuel, and supply chain logistics to over 13 million people. Consider scale translation. Lateral ground displacement will reach between 4 and 8 meters instantaneously. No physical material engineered by humans can stretch 8 meters in 2 seconds without severing. Highway links connecting coastal basins to the interior will be offset laterally, shearing asphalt and dropping overpasses. Main rail lines moving thousands of tons of freight daily out of West Coast ports will twist into unusable steel loops. Major municipal aqueducts, concrete tunnels carrying billions of liters of fresh water from northern snowpacks into urban reservoirs, cross primary fault lines directly on surface traces. When a gate-jumping rupture occurs, those conduits will be sheared cleanly in half. Daily water flow carried by those severed aqueducts equals annual municipal consumption of a city the size of Calgary or Edmonton. Within 60 seconds, millions of residents will be cut off from fresh water supplies. Repairing a severed concrete aqueduct under mountain rockfall is a multi-month heavy engineering operation, forcing strict water rationing within 48 hours. High-voltage transmission corridors crossing mountain passes rely on steel towers anchored into bedrock. Violent surface accelerations exceeding 1.0 g will trigger structural collapse of key transmission pylons, tripping regional circuit breakers and cascading across the western interconnection grid to plunge entire regions into blackout. In daily life, immediate escalation arrives on mobile phones through alert-ready systems and emergency broadcasting networks. Shake Alert, operated in coordination with Natural Resources Canada and partner agencies, detects initial non-destructive P waves, broadcasting automated signals to trigger audible alarms. For people 30 kilometers from the epicenter, that alert provides 10 to 15 seconds of advance notice before violent S-waves arrive, allowing industrial controls to lock down gas valves, transit trains to brake, and backup generators to spin up. Economic ripple effects span the continent. The Port of Vancouver and West Coast shipping hubs rely on uninterrupted rail and trucking connections through inland mountain corridors to move consumer goods, manufacturing components, and agricultural exports. severing transport arteries for weeks, chokes supply chains from British Columbia to Ontario, causing immediate shortages on retail shelves thousands of kilometers away. On the 18th of April 1906 at 5:12, a single continuous tear along 477 kilometers of northern plate boundary released 60 years of strain in less than 90 seconds, moving surface rock laterally by up to 8.5 meters. Today, stress recorded along the southern expanse of that same boundary is vastly higher than baseline levels measured prior to 1906. We must separate scientific truth from sensationalized alarmism. Titles often treat high-stress measurements as a prediction of imminent doom. That framing is false. Maintaining credibility requires stating the honest boundary between established science and what remains unresolved. What is conclusively established is physical force stored in rock. Through paleoseismic trench samples, tree ring growth chronologies, and four-dimensional modeling, geophysicists proved shear stress along the southern boundary and adjacent San Jacinto fault line reached 3.6 megapascals, the highest in a 1,000-year reconstruction. It is established that the structural gate beneath Cajon Pass sits in an unlocked state, and if a rupture jumps that gap, the resulting event will release magnitude 7.4 to 7.8 energy, generating up to 60 seconds of intense shaking. What remains unresolved is the precise moment of failure. Earthquake prediction remains impossible. Accumulation of elastic strain is a certainty, but the exact trigger converting static friction into dynamic sliding operates on non-linear chaos dynamics. As researcher Kate Scherer noted, the earthquake could initiate today, tomorrow, 10 years from now, or 30 years from now. At the temporal scale of deep geology, those intervals are indistinguishable. The physical system operates on strain thresholds, bending silently while storing energy from 5 millimeters of annual plate displacement. 3 checkable developments will tell us which way this situation is moving. First, monitor seismic event logs maintained by the Canadian Hazards Information Service and partner networks for sudden clusters of microseismicity at depths between 8 and 15 kilometers directly beneath Cajon Pass, signaling that static friction holding the structural gate closed is destabilizing. Second, watch for formal updates to GPS displacement vector maps published by Natural Resources Canada and global observatories. Localized acceleration and surface strain rates along the San Jacinto junction indicates deep crustal creep is transferring additional shear stress into the locked upper zone. Third, keep an eye out for formal advisory updates or structural assessment mandates issued by agencies like Public Safety Canada and provincial emergency bodies, marking the transition from academic modeling to active preparation. Until one of those events occurs, the situation remains precisely what data says it is: a continent-scale fault system sitting silently at a 1,000-year stress peak, fully loaded, unlocked at the junction, and waiting for the physical break that will reshape the landscape above. The earthquake is a mechanical certainty, but the catastrophe is optional. Let us know in the comments below which region or province you are watching this from today. If you found this technical investigation